Okay, so we're going to get to what, so today we had the, so this will be board 1. Okay, so today we had this talk by Joachim Koch, and he talked about polynomials in many variables. We're going to get to polynomials in many variables tomorrow. That's a very easy application of, like it's kind of in there when you look at comonoids in poly. But today we're going to look at monoids. We're going to look at the composition product and then monoids in that most of the day today. And we might start comonoids, we might not. So this is just board 1. That's why that 1 is there. Okay, so the last monoidal structure, or the most important probably, is the one that Joachim talked about today, other than plus and times, which is kind of what generates poly to begin with. The next one, tensor, comes up all the time in dynamical systems. But then we have composition. So we can compose polynomials. And Joachim wrote it today as compose with a circle, because often we want to think of often we want to think of these as functors. But in this class, we've seen that these things can just be data structures, like for wiring diagrams and all sorts of other things. And so for us, polynomial functors are objects in the category, not morphisms between things. And as objects, we don't want to call it composing, because composing, we want to reserve the word compose for morphisms. And we're in the land where Q and P are objects. So when we want to compose the functors, we're going to use this triangle symbol to mean what, if you draw it fast, by accident, you see a circle. So it's not like scary. It is the circle. But we're going to reserve circle for composing morphisms. You know, if you have a map of polynomials and another map of polynomials, phi and psi, you could write psi composed phi, or phi semicolon psi. Those are the same, and we'll talk about composing morphisms. But this we'll call substitution product. It's a monoidal product on poly. So it takes poly times poly to poly. It's sometimes I call it tri for like triangle, because in my like LaTeX code I write \tri. It's not tri like try. So slightly, it's just really long to say substitution product versus tri. So it takes P and Q and sends them to P tri Q, or P composed Q, or P substitute Q. So the reason I liked this symbol was because of how it looks when you draw polynomials as those corollas that Joachim talked about today. But first of all, do you agree that this is associative, that if you take P composed Q, then compose that with R, you get P composed Q composed R? Well, yeah, because they're just functors. Well, sorry, I asked if you agree, but then I saw a bunch of people nodding, so I was like, okay, you get it. But what is the unit for this? The identity functor, which we denote by what? Yeah. Okay. So y tri p. Okay. So here's how these work. You can draw polynomials. Joachim draws them. So now that we have him in the context, like now I'm talking about him all the time. But he might draw these things like this. Whereas I found when I was thinking about these things that I didn't want to have that bottom thing. I just wanted like to look at them like this. So here's a polynomial. Actually, yeah. And this would be the polynomial y cubed plus y squared. And maybe we could do like y squared plus 1, or, you know, y squared plus 2y would be like one of these labeled, you know, 1 or something, and one of these labeled 2. Plus 1 would be with a dot. Really, they're all tagged with like some coefficient, because this is a sigma, a big sum, and that adds these tags. But sometimes it's annoying you don't have to put the tag if there's just one. Is that okay? If there's just one thing with 2 in it, I don't write the tag because it's the only one it could be. Okay. So when you try to compute, so let's do y squared plus y composed y plus y cubed plus 1. So in polynomial arithmetic, what you do is you just plug this in for y. So it's y cubed plus 1 squared plus y cubed plus 1. And that's isomorphic to y to the 6th plus 2y cubed plus 1 plus y cubed plus 1, which is y to the 6th plus 3y cubed plus 2. OK, but now let's draw it the other way. There's no reason to write, well, OK, 3y cubed plus 2. OK, so now, but what this looks like is you draw y squared, and then on top of each of these leaves, you put one of the other guys. OK, so I'm just going to do it and not talk about it. So this one, sorry, this one is y squared plus, y. And this one is y cubed plus dot. And so what we do is we just draw all possible things like this. What else do we have? We have this, and we have this. OK, so these are, do you see what I did? And so now what I want to do is I'm composing. And when you compose, you kind of drop out the information of like the middle thing. Remember we talked about that yesterday? I mean, everyone already knows this in some sense. But if you want to go from A to B to C, you drop out knowledge of the middle part, right? You take F compose G, and now you go from A to C, forgetting how you got there. And so when you forget how you got there, this one becomes 6. This one becomes 3. This becomes a dot, 3. This becomes dot. This becomes 3. And this becomes dot, because we drop out the middle thing. How many open leaves are there on this? 6, 3, 3, 0, 3, 0. And so we get y to the 6th, y cubed, 1, y cubed, and 1. And that is the thing we said we were supposed to get when we did it by usual old-fashioned polynomial arithmetic. So questions? See a little bit. We wanted to compose these two. We did the plugging in thing. This triangle looks like plug in, right? It says take this and plug it in there. That's this directionality to it. We composed two functors. We plugged in. We calculated. And what we realized is it's the same thing as putting these little guys on top of the open leaves of these little guys. Question? Yeah. Nate?
Oh, yeah. I was just confused by that last one and that first line of double corollas.
This one?
Yeah.
This one was this guy.
Okay.
So I took this one here, and I tried all the combinations of putting one of these on top of it.
Okay, fair enough.
And then I got to this one, and I tried all the combinations of putting the other one on top of it.
Yeah.
Do you guys want practice with this? Yeah. OK. So, I mean, you could choose your own. It's just that it's very easy to choose too big of a thing. Well, let's do y cubed. I'm afraid I always do too big of a thing. Maybe I'm just projecting. Y squared plus 2 composed y cubed plus y plus y. Okay, try that on your paper. Yeah, Priya?
I think it will be helpful if we use different colors for the
for the two things. Okay. Well, try this. Yeah, question?
Yeah, I want to test my intuition.
Yeah.
So I know that in the context of dynamical systems, this is like speeding up.
Yeah, that. At some point along the way, I thought that was a nice way to look at it. Yep.
Yeah, I think it's good because it sort of represents the functor that you get if you handle all possible cases of how you could step twice into the resulting function.
That's right.
This has a very strong, especially because
Thank you. No, you're good. Too hard. Keep going.
because you're counting, like, the resulting polynomial only treats the trees that reach the length of however long your composition is. So
Well, or puts a dot. It terminates. Yeah.
yeah, and that really does feel like, okay, these are all the possible senses that you could walk that would survive to the end.
Yeah.
And so like it privileges a certain way of thinking of it in like steppy, in a steppy way, like you're composing two polynomials is like has a feeling of steppiness, even though there's no dynamics yet. You need a lens for that.
Okay. Are you asking a question or giving like commentary, or can I just ask?
Yeah, I'm just wondering what you think of this intuition, if it's.
I think so. Yeah, I think it's okay. Yeah, you're kind of doing a two-step process. Yeah.
Yeah.
Yep. I feel like I missed some. What I heard Sophie.
Oh, nothing. I just got confused about that.
Okay, I think I don't know, one. I don't know where I am anymore. Two. Oh, where am I? Oh yeah, two. Okay. Two. 2, 1, 2,
It's big.
2.
But it's nice because it's like it forces you to
Okay.
handle everything.
Y, we think this is y to the 6th plus y to the 4th plus y to the 4th plus y to the 4th plus y squared plus y squared plus y to the 4th plus y squared plus y squared plus 2. That's what my calculation with trees tells me the answer should be. Did anyone try it themselves and get the same or different thing? So I got y to the 6th plus 1, 2, 3, 4 y to the 4th plus 1, 2, 3, 4 y squared plus 2. Yeah?
Yeah. So for this example over here, which ones reduce to like something without direction for this?
If this one and this one, all the directions have been dotted off.
So if you start off from a place, okay, so it's basically like those are like deformed, like into they just can be like
Yeah, they all
reduced.
reduce down, yeah.
Okay,
It just counts the number of open leaves. Yep.
Yeah, okay.
Just counts the number of I didn't do what you said. Sorry. I'm bad with color. Okay, and so the reason when I originally was like, for me, I'm just like very notation conscious or something, and this was like P composed Q. It's like this one's P, this one's Q, and the triangle is telling you that it's branching up. There's P on the bottom and Q on the top. So P is on the bottom, Q is on the top. So it's branching upward. Does that make sense? So the notation works for 3 reasons. 1, if you draw it too fast, it's a circle. 2, it looks like you're plugging this into this, like it's kind of going that way. And 3, it's drawing trees like that. So that's kind of where that came from. This is board 2. Sure. And it also emphasizes it's not symmetric, so somebody can write this. I usually get very concerned that they don't mean what they're saying and they are just forgetting like the notation I like. And but this could be written to mean plug P into Q. And so I kind of like the idea that non-symmetric tensors should get non-symmetric symbols so that you can distinguish between which direction you're doing it. Okay, questions on triangle? Okay, so what is P? Let's say A is a set. Suppose A is a set and P is a polynomial. By the way, I asked questions and I didn't really pause, but if you have them, just ask at any time. So what is P composed A and what is A composed P?
It's like plugging in A for where Y is.
Yeah. So if for this one is plugging in A into the open leaves. So if P was like, y squared or something, and a was like 3, then it would be 1, 1. Shoot, I have to do 9 now. See, I always, okay, 2. 1, 1, 1, 2, 2, 1, and 2, 2. Like basically, A is 2 dots, one labeled 1 and one labeled 2. So we're just popping those 2 dots onto the 4 possible places, and that's why we get 4, because 2 squared is 4. Questions? So we have been writing P of A as though P was somehow, as though P was like a functor. But P is not a functor. P is a data type. It's a polynomial. It's not, okay, so you can turn it into a functor anytime you want. It is a functor, but the one way to think of it, just living inside of poly, I was kidding about it not being a functor. It's, all these things are functors. But inside of poly, it's just an object. It's just kind of a thing with positions and directions, or positions and momenta. I kind of like that idea from Joachim today. And A is just a polynomial, but it's like a special one where it has no leaves. It's just a polynomial with just dots, just constant. And so we can write P of A. We don't have to write it that way anymore, but we could write P composed A. And now we're just only living where parenthesis is just a way of bracketing things and not application, which is I find nice. We don't need to overload this parenthesis term. So P of A means P applied to A, P composed A, P trie A. Oh, what about this one? It's just A. Because it says for every open leaf of this, like over all of the different summands of A, for every open leaf, put a P on top. Well, there are no open leaves, so this one is just A. Questions? Yeah.
Yeah, so one thing I'm struggling with that P composed A. So when you substitute A into P, think of it as a polynomial, and it fits, every place there's a Y now becomes an A.
Yeah.
For that, you don't really think of it as a tree in the same sense anymore.
I mean, you can, because you have this tree, and at every open leaf, you pop in an element of A, because that's what we said we would always do. So if we have, yeah.
So, but the open leaves are like up in the exponent, right?
You're worried that it doesn't work, or you don't understand the process? You're worried it doesn't work, right? So so could you give me a polynomial P and a set A for which this procedure does not do P of A?
Well, I mean, I'm just confused about the most basic case. Let's say P of Y equals Y squared. Right?
So, yep, Y squared.
Yeah. So I like to draw that normally as, this nice little corolla. Yeah.
And like A is like, red, blue or something?
Right.
Or red, green, blue?
Right.
Okay. I don't have blue.
So,
I don't have green.
With the corolla, I think of like the leaves being associated with direction. So they're up there at the exponent level.
The leaves are, what did you say? The leaves of this thing?
Yeah.
Each one of them, we're going to pop on one of these. So we just get like
Okay.
red, 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 red. Uh-oh, I don't know how I'm doing this anymore. Red, blue.
Yeah, no, I understand that from like
green.
a corolla superposition thing. Like
Okay.
That is no problem for me.
I guess I'm sorry I'm missing your point.
But when I'm substituting it in, I think of it now, okay, I substitute in 3 for Y, and I get 3 squared, and like the 3 isn't up there in the upper part.
The 3 isn't up there?
It's 3 squared.
So we do get the 9.
Yeah,
Or
I
3
know,
squared.
I
Sorry,
know,
yeah.
I know, it's just,
Darn,
it
sorry.
doesn't appear at the top.
It doesn't appear at the top?
That the leaves are like higher, like
Yeah.
like visually, the
Yeah.
thing that's the 3-bit is higher than the thing that's the 2-bit.
Yeah,
The
that's
thing-
what's troubling me.
The thing that's the P bit is higher.
It's not a
Wait,
huge
what's it?
barrier, just
Wait,
I
say
have
it.
to
What is
avoid
it?
thinking
Say it again,
about that
Sophie.
way.
It's that like visually, the part that corresponds to the 2
Yeah.
in the Y squared
Yeah.
is below, like visually below
Yeah.
the thing that corresponds to the 3.
Yeah.
The thing that course. Yeah, because this tree is growing up. right? Is that why? The trees are growing up from here.
Right, I mean, like, when I think of it as sticking them on top of each other, it's all fine.
Yeah.
When I think of them separately, not in a tree-like corolla fashion, substituting in, it's all fine, and I can compute the actual value and all that, and things are happy. But
Okay.
when I try to mix the two, think like, I'm gonna substitute in, and I get 3 squared, and I think, I'm gonna draw a tree for that. It's kind of weird to think about, okay, so I have branches, 2 branches.
Okay, I got an idea. Maybe this will help, maybe it won't.
Yeah.
If it doesn't, then we'll have to try again.
Yeah,
So let's say P is the sum over all positions of P of the product over all directions there.
yeah.
Or, I almost want to say momenta. I want to practice with that and see if I like saying it. So Q is this guy, Q of 1,
Yeah.
product over E in Q bracket
Yeah,
J of Y. And now we want to take P composed
yeah.
Q. The formula is, well, you plug in Q for Y.
Yeah.
So it's that thing.
Yeah.
So it's pretty easy. It's like ready to go, right? So these are all the little corollas.
Yep. Yep.
These are the leaves.
Yep.
This says for every leaf, pick
Yep.
another corolla.
Yep. I'm perfectly
Darn,
happy with
didn't
that.
work. Okay, so what is,
So it's probably, I'm just creating, probably I just need to think of the two separately. I either think of it as tree stacking on the one hand, or I think of it as substituting a variable and evaluating that, and there do the
Yeah.
two meet.
yeah, but don't they meet right here? Substituting this into there is on every open leaf popping one of those.
Yeah.
There's one last part in this procedure, which is that we then do this collapsey thing, where we forget the order.
Right.
And what that is the distributive law here.
Yep.
No. So that is the sum over I in P of 1 of the sum over all functions j that take P bracket I to Q of 1 of the product over all D in P bracket I of the product over all E in Q bracket J as a function applied to I of Y. So this is the sum. So a position of P composed Q is you choose a position of P, you choose for every, I'm just rewriting at this point, but no, I'm not. For every direction of that position, for every one of these, choose which corolla you want to use. And then the directions there are a choice of direction in each one.
I have a goal.
Goal.
Yeah. I feel like I've always worked really hard to remember what's on the right-hand side of P try Q on your first line. And when you substitute it, it's like super obvious.
Yeah. Okay, great. Yeah. Great.
This makes it clear also that if the directions at that position are 0, then that sum disappears.
Yeah, if P bracket I had 0 in it, then this becomes an empty sum and this term goes away. Yeah. Great. Questions? But this is just composition of functors. So it's composition of functors, but it has a form that's comprehensible. Yeah. Any questions?
When we collapse it down,
Yeah.
any that didn't make the cut, they didn't go all the way up, disappear.
Well, we still count them, but this sum
Okay.
is
yeah,
a sum of
they
empty.
appear
They,
as dots.
this becomes 0,
Yeah.
and then they appear as dots.
Yeah.
Yeah. Yeah.
One way I like to think about it is that it's like a survival thing. So like if
Yeah.
If you're composing two polynomials,
Yep.
whatever leaves reach the length of 2
Yeah.
are going to survive as leaves. Otherwise, they become dots.
Yeah. So you can think of these as like strategies for one player, and that player has like 4 positions they can be in, or 4 orientations to the world, or whatever. And then for whatever happens to them, they have a new strategy. Like does that make sense? I can be, like this, or whatever, and then I look around, I see something, and then I switch. So it's all possible two-step strategies, if that makes sense. Yeah, okay, we'll get there. We'll keep moving along. I don't know if we'll explicitly talk about strategies, but when we talk about comonoids and things, it'll kind of be there implicitly. Okay, so I wanted to mention some facts. Okay, do you agree that P1 plus P2 composed Q is P1 composed Q plus P2 composed Q? So see if you can think about why that would be. And same with times. And yeah.
Can you say what times is in terms of tree? Like the first one I sort of think about in terms of
Yeah, trees. Yeah.
say what P1 times P2
Ah.
like as a tree?
Yeah, what is P1 times P2 like as a tree? So if P1 is, like that, and P2 is like that or something. So y squared plus y and y cubed plus y plus 1, then P times Q, P1 times P2 is you pick a position from each. So you pick a position from each, and then you add. Darn, yeah. Maybe I'll draw it like I don't know.
You gonna put it in a grid?
I don't know what I wanted. In a grid?
With
Okay,
two
yeah.
different colors.
Yeah, in a grid, yeah. Okay,
Well.
okay. P1 is that, and P2 is, what did I say? That or something?
Yeah.
Then we have 5, 3, 2, 4, 2, 1.
That's times, right?
That's times.
And in that 5, 2 of them came from the one on the left, and 3 of them came from the one above.
Yeah. Yeah, you add exponents. Yep, and for tensor, I guess we might as well do tensor. Is 6. Then you multiply. 5, 6, 1, 2, dot, 1, 2, 3, 1, dot. So tensor, is y to the 6th plus y squared plus 1 plus y cubed plus y plus 1. Sure. All right. So, I mean, we can appeal to the fact that these are functors anytime we want.
Sorry,
Yeah.
I was just writing. This one is
Tensor.
tensor. Yes.
Okay. This is a bit confusing, but I hope it's okay. So these really are functors. We can think of them that way when we want to, when it's convenient. And when you add two functors, what you do is you just add their values on anything. So if I add two functors and I add them applied to Q of something, then I just take P1 of Q of something plus P2 of Q of that thing. Does that make sense? Like we said before that F plus G of A is F of A plus G of A. That's the definition, or that is the universal property. It's either the definition or the universal property of coproducts in the category of functors. Well, if somebody told you, let's replace that G with an F2. If somebody told you that A happened to be G of something, and they said, oh no, I've got a much more complicated situation for you. It's actually G of something. Well, that wouldn't be scary at all. I mean, it's just, just because it's G of something doesn't mean we're going to treat it differently. And so if F1 was P1 and F2 is P2 and G was Q, we can see that this has to be true. Does that make sense? We're just plugging in, substituting. Or you could calculate it yourself with some pictures of corollas and see that like each one of these corollas would be sitting there, and then these would be sitting next to them, and you'd pop Q's onto either one. Yeah. And so it's easy from that point of view too. This one, same thing. We told ourselves earlier what product of functors meant. It means, well, it's a universal property of products, or you just put times is where their plus is, and you get the same answer. It works out well. And so we know this thing has to be true just because of like how functors work in the same way we did this one. But you could also do it by thinking about corollas and do some mind-bending corolla exercises. I don't know how mind-bending they are. I'm just saying like they might be. I haven't thought about it yet. But they're going to work. So it'll be mind-correcting. It won't be mind-bending. It'll be mind-correcting probably. But any questions? Yeah.
Yeah, so I was shaken by something that you did or said 2 days ago.
Okay.
I believe it was 2 days ago. Maybe it was yesterday, early. Maybe it's not an issue, but maybe you could help me figure out if it would still be an issue. For those functions there, P1 plus P2,
Yeah.
for example, if that were instead of plus, if it were tensor, that would also be true.
This would not be true.
Oh, it would not be true
No.
with tensor.
No.
Okay.
And it's not true on the other side. It is not true.
Right, on the other side.
P1,
Yeah,
P
indeed.
composed Q1 plus Q2 is not like, well, I guess it's kind of like P of Q1 plus
Yeah.
P of Q2
Right.
does map into this, but it's not an isomorphism.
Right, but if instead of P1 plus P2, you're saying that wouldn't work for tensor, that
Yeah, this is special about plus
special
and plus and
plus
times.
and
Plus
times.
yeah.
Okay,
Mhm.
yeah, that's the thing that.
And it's special about being on the left of the tri.
Yes,
Yeah,
indeed.
triangle. Yeah.
Indeed. And why is it that somehow shakes my faith in the universe?
Yeah, you're scared that like, how could a theory as beautiful as poly not have a nice interaction between tensor and tri?
It's something more
No.
elemental than
Okay.
that, because I just think like, isn't it just a matter of substituting Q in for each of those? So how could it not be the case that they're
Okay.
equal? That
Well, let's
it's
tell
like
what. Let's say
P1
what.
of
Let's
Q,
yeah.
blah,
Let's say what is the
P2 of
case.
Q.
Let's say what is the case,
Okay,
and then we'll use that to develop a counterexample to the other one.
great.
Okay. So what is the case is what's called duoidality, which says that there's a natural map from P1, and then you draw a tree growing up to P2, Q1, and then Q2, versus maps nicely to P1 tensor Q1. Do these at the same time, and then do P2 and Q2 at the same time. So this is the nice law between tensor and tri. And I can take you through it on positions and directions, but you have to watch carefully my fingers moving. So I probably should wait for you to be ready. You could also do it yourself.
First, I want to ask, what is duoidality? I guess is monoidality.
It means we have two. It means we have two different monoidal structures, and they interact. So in any monoidal category, sorry, for any category in the world, if you've got a monoidal structure and plus, then you'll have like P1, P2 plus Q1 with your whatever monoidal structure you want in the world will go to like this sort of thing. So like for plus and times, like you can always do, they're always duoidal, but it's always kind of uninteresting. Ouch, where am I? There we go.
Will go, you mean there exists?
There exists a map that has lots of nice properties. Yeah, there exists this map, and you can count on it to, you know, if you see it in a proof and you find some error somewhere, it's not going to be because you use this.
It's a canonical map.
It's a canonical, beautiful map that, yeah, you don't really have to look there usually for where your mistake could be. Yeah.
Do you think there are more natural maps from?
I doubt there are more natural maps that work for all P's in P1, P2, Q1, Q2. If there was, I'd be shocked to my core, as Nate would say. But yeah, this is the one that works naturally over all P1 and P2 and Q1 and Q2. I'm guessing I would guess it would be the only one. I don't know.
Can you prove this on the computer by taking P1 by starting? So you're using the distributive closure of one object, right?
Yeah.
And
Well, yeah.
take the distributive closure of four objects, so a discrete.
I don't know. I can't answer that on the fly, how you would do it that way. I think I wanted to talk about the how this looks on positions and directions. I'm sorry to cut you off, but I'm sure I won't be able to do it justice. Okay, so are you guys ready to like watch fingers moving and stuff? Okay. So on this side, a position is a position of P and for one, and for every direction, a position of P2, and a position of Q1, and for every direction, a position of Q2. Do you guys agree?
Mm-hmm.
From that, can you tell me a position of P1 and a position of Q1? So this is a position of P1, and for every direction, a position of P2,
Exactly.
and a position of Q1, and for every direction of it, a position of Q2.
Right.
And I need a position of P1 and a position of Q1.
Just project.
I just take I told you I had them, so
Yeah.
take them. So I'm going to write this. So if we have I1, I don't know if you guys, I have notation that a lot of people don't like, so I don't know whether to write it or not. But let's just keep going. Okay, so now, given a direction there, so I have a position of P1 for every direction, a position of P2, a position of Q1 and for every direction of a position of Q2. Now I have a position of P1 and Q1. Given a direction there, well, a direction here is a direction of P1 and a direction of Q1. So if I had a direction of P1 and a direction of Q1, then this guy's ready for action, this one's ready for action.
Yeah.
They'll each be able to hand you a position of the next one. And so we get a position in this one, a position of P2 and a position of Q2. And then, given a direction of this thing, a direction of a trie is just a direction of the first and then a direction of the second. Do you remember that?
Yeah.
Yeah. If you have P trie Q and you have a position in it, then that means you have a position in P, and for every direction of it, you have a position in Q. What is a direction there? Well, you pick which P branch you're on. Once you do that, a Q opens up, and now you pick which Q branch you're on. Okay, so now we have a direction of this one, which is a direction of P1 and a direction of Q1. And we have a direction of P2 and a direction of Q2. And we need a direction of this thing and a direction of this thing. So we take the direction of P1, something opens up. We take the direction of P2, take the direction of Q1, something opens up. We get take the direction we had of Q2. Should I try to notate this?
So that was the backwards
That was the backwards, yeah.
arrow?
Yeah.
Maybe draw it as
Draw it.
as two parolas.
Oh, man.
Sorry.
Or could you, I think it's it's an much easier request to just ask you to restate your last one or two sentences.
Okay.
For the backwards map.
Yeah. We have a position over here, a position of P1 and a position of Q1.
Yes.
And for every direction, a position of P2 and a position of Q2. And now we take a direction there.
Yes.
Okay, well, it's a direction of P1 and a direction of Q1.
Yeah.
And a direction of P2 and a direction of Q2.
Yeah.
And so we just get the 4 things we need.
Yeah. It just sort of maps back.
That just
to
map
the
back in a very
corresponding-
easy way. Once you like take the time to go through it slowly, you'll get it. Like this one is not so bad. Yeah. The only hard part is how to notate it, and I notate it as, I'm going to use i's even though I like p's better. I and p of 1, and then I2 that takes P1 I1 to P2 of 1, comma, J1 in Q1 of 1, comma, J2, that's a function from Q1 J1 to Q2 of 1. This maps to I1 J1. What did you say?
This is map on positions.
On positions. I1 J1, comma, the function that takes so I need a map from P bracket I1 P1 I1 times Q1 J1 to P2 of 1 times Q2 of 1, and I use I2 times J2. I2 times J2 was exactly what I needed. And then given a direction here, this is a position, given a direction would be a D1, E1, and then like a D2, E2. So where is D1, E1? D1, E1 is in P1 of I1 times PQ1 of J1, comma, D2, E2. Anyone know the type of this thing? P2.
Square bracket, and then we need a position of P2, so we're going to get it from I2. But we need to plug in something. We need to plug in a direction of I1, which is D1. Times, and the same thing but with the Q's.
Okay, this thing is a direction. And it goes back to a direction over here. It goes back to a direction of this one and a direction of this one. Okay, a direction of P1 composed P2 is a direction of P1, which I'll take to be D1, and then a direction of P2 bracket I2 of D1. But that is what we had here. So D2 is okay. Nothing, as you can, so just looking at, like, there's a lot on the board, but just looking at what we have an I1 and an I2, J1, J2. Where does it go to? It goes to I1, J1, I1, J1, I2, J2. It kind of just like switches the order, which kind of makes sense because things are kind of switching. And then it takes a D1, E1, D2, E2 back to a D1, D2, E1, E2.
Sorry, it switches the order where
Well, you see here we had D1, E1, D2, E2.
Yeah.
Well, now we have D1, D2,
Oh,
E1,
okay.
E2.
Uh-huh.
It sounds almost the same, but it's swapped right there,
Mhm.
kind of thing. Yeah.
So I got lost in where did D and E come from? I was.
Those were directions of this thing.
Mm-hmm.
Oh, I see.
Yeah. All the data is like the same. It just kind of switches order. Yeah.
It doesn't trouble you that like I1 is like an index and I2 is a function?
No, it doesn't. So like if I say someone's a father, you have to say father of who? But you don't have to. They're just a father. Father is a function from people to. So I like if I have a map from A to B,
Yeah.
like I think B is a good name for such a thing.
Okay.
It's B of A would be a B.
Uh-huh.
Every time I write B of something or B
Right.
sub A, I know it's a B term.
Right.
So I like this to be the name. And also if you have a single element of B, it's convenient to call it B. So it's just a generalized element, taking that seriously, that if you are landing somewhere, it's nice
Yeah.
to notate it by the name. I personally would be calling these capital Ps in my preferred notation,
Right.
but people here like me to call them I2s.
Yeah, and it didn't trouble me that it was a function per se, but just that you have two different, one's a function, one's
An
index.
element, but if
I
you
think
with
your
this,
point is there are ways of getting it.
Yeah.
And you could treat it as one into, like you could have I1 be a function too.
yeah, I like to look at it and know
Yeah.
I like to look at the variable and know the type as well as possible.
Yeah.
And so like calling this a function, if you call it F,
Yeah.
you don't remember who its target is, but when you
Yeah.
call it B, you know it's a type.
Yeah,
of
but
type.
you wouldn't make I1 a function for the same
Well,
reason?
if you want to, you can.
Yeah.
Yeah.
Okay.
So in general, if I have product over A in A of BA,
Yeah.
I might call this B.
Yeah.
Okay.
Thank you.
Sure.
So intuitively, it's like on the right-hand side, you have a pair of systems, or you have a pair of interfaces and a pair of interfaces.
Yeah.
There's many. You can visualize like ways of plugging those into each other, but the natural one is to plug in the top one and the bottom one,
Yeah.
which is the left.
Well,
hand.
actually, there's lots of good ways. Yeah.
There's like
Yeah,
lots
lots
of good ways.
Yeah,
to
yeah,
imagine,
yeah,
But
yeah,
sort of like the
yeah.
natural one is to
Well,
just plug in
yeah.
the top one and then also in parallel plug in the bottom one, which is
Yeah.
what maps into this.
Yeah. Yeah. That's a good one. Yeah. Okay, did you still want Nate to understand something about tensor?
Oh, well,
So if we have P1 tensor P2.
well, it wasn't actually so much about tensor, it was about this
Oh.
whole issue of how far does this general rule go that if you have an operation combining like P1 and P2, and then you substitute something in to that result,
Does it distribute? Yeah.
Yeah.
Yeah, it does not for tensor.
yeah, so it's something
I
very
don't know.
nice about plus and times that it
Yeah.
does.
Yeah.
Yeah, okay, yeah.
I would like to know what is just P1 tensor P2 composed with just a single Q.
Yeah, great. Yeah.
Okay.
Oh no, I don't know how to do. That's not. It's not nice. Has no. I don't think it has any nice properties. You could try, but there's another one that does have nice properties, which is composing. So what I want to say next, I guess, is that there's a map from P tensor Q to P tri Q, and I call it indep for independent. Like if P and Q are in parallel, and P compose Q is like kind of P then Q, or P at the bottom, Q at the top, there's a map that says, well, at every leaf, I'm waiting for something, just pop the same Q on over and over and over. So where does this come from? The way I know I can get such a thing is does anyone see how to use duoidality to get this map?
Can you just use like Y?
Why? Where?
Yeah,
What do you want me to
Yeah.
write?
yeah.
Why?
P tensor Y. P tensor Y.
P tensor?
sorry, P compose Y.
P1, B1.
Yeah, P compose
P1.
This? Yeah.
Yeah.
Tensor? Q applied,
Q
Wait,
try Y.
Y applied to Q.
y tried Q, yeah.
On the other hand,
Oh,
couldn't
wait.
you also do y composed with p and
Yep.
and
Yep.
q composed with y?
Yep. So this is P try Y, tensor Y, try Y tensor Q, which is isomorphic to P try Q. Great.
Wait, why did the Y,
Yeah,
why is it Y try Q on the left? It's,
Priya told me to write Y try Q. Oh, right. And this is P tensor Q. So you have P
Right.
tensor Q
Yep.
Yeah.
going to P try Q.
Yeah, you could put it in either order. P try y is the same as y try p.
Yeah.
Which
Yeah.
is a thing of beauty.
sorry, I'm confused as to why is it not, could you not have done P try Y tensor
Yep.
Q try Y?
Oh, no, I couldn't, that's one I couldn't have done because I would have gotten, okay, the question was, what if I did P try Y tensor Q try Y? Well, I know I can get that to P tensor Q try Y,
Which
Y
gets you back
tensor
where you
Y.
started.
which gets me back where I started, and I didn't really get to where I wanted to go. Like, yeah, you can use duoidality any way you want, but we wanted this. And what your suggestion did was just got us back to P tensor Q. So you just got us the identity. So I'm going to just give you an exercise. Can you get a map from this to P1 composed P2 tensor Q2 composed P3 tensor, what? Q1, P3 tensor Q2 composed Q3 composed Q4. I think I'm just trying to tell you how to use duoidality. I mean, actually, let me just do a different thing. Well, I don't know. Let's do a different. Let me do a different one. You can do the one I just said. Q2 composed P3 tensor Q. Let's do another one. Q3 composed P3. Can you get this weird map? I'll just give you a few minutes. You can either work on this exercise or think about anything you want. We're just going to take like a 10-minute do what you want time. Try to focus on poly unless you need personal time or whatever. Okay. Yeah. Okay, did anybody find a map like this? Or was it just too weird and you didn't care? That would be fine. But can anyone guess? Maybe I should do this one first. If you have P1 composed P2 composed P3 tensored with Q1 composed Q2 composed Q3, do you believe that you get a map to P1 tensor Q1 composed P2 tensor Q2? Here's what you do. You parenthesize two of them. Think of it as just a P. Like, just think of this thing as P. And then you do it, and then you unparenthesize it, and you get the last piece. Like, you just fold two of them up so you don't look at it, shut your eyes to it, and then unfold later. Do you guys believe it? If you don't believe it, this is an exercise. Find one of these. But really, it's just about parenthesizing. Okay, but then if I want this crazy map, then I just like put a bunch of y's everywhere. So like to get this, I say that this is isomorphic to P1 y P2 Q1 y, what? Yeah, y P3 y Q1 Q2 Q3 Q4. Like if I just insert y's where I don't want some action to happen, then you can like, as long as you keep the order the same, everybody's happy. You see it? So what did I do? I just inserted y's various places. I inserted a y here, which meant that when I do this, longer duoidality thing with P1 and y, I get P1, secretly P1 tensor y. So that's P1 tensor y, P2 tensor Q1 is what I wanted, y tensor Q2 is what I wanted, y tensor Q3 is what I wanted, P3 tensor Q4 is what I wanted. So I'm allowed to kind of like march through them as long as I keep the order the same, and duoidality gives you that sort of structure. The reason we like these things is because often you're doing computations and you have an intuition that something should work. Let's suppose you're working with polynomial functors because you want to model dynamical systems or whatever sort of thing. And you're like, oh, this should work. Well, you don't want to invent, like it's nice when you can just use properties like duoidality to reconfigure things so that your intuition, this is like the rails, or that helps you track your intuition and never leave safe ground. Yeah. Did someone make a noise? Okay.
I have just like a general
Yeah.
discomfort with, because I don't understand the duoidality map. So if you just show me an example where in one case it's the identity and the other is in-depth, which has a really deep intuitive meaning.
Yeah.
It's just, I'm a little, like duoidality.
Okay.
Two things that are isomorphic does not give you, it feels like it shouldn't touch anything, but it does.
Two things which are isomorphic. What did you say?
Well, like if you apply duoidality to the thing on, the tensor on the left-hand side of duoidality.
Oh, over here? Yeah.
No.
For in-depth? Yeah.
That thing is isomorphic to the left-hand side of the other.
This one.
Like.
Oh, this one.
Yes. So this is isomorphic to this.
Yeah.
This is duoidality.
But it's not an ISO, it's just a map. So yeah, it is duoidality, it's a map.
Is this not the identity?
No, these are not the identity. Duoidality is not an ISO.
Isn't it just mapping?
It's just a map. It's a one-way map.
Okay,
This is bigger. This is, I think, always a bigger thing than that.
Okay.
Yeah.
Okay. Sorry.
Yeah. Like P, so here's what's happening. Maybe this will help. P tri Q. Okay, let's say you add P tri Q. Yeah, P tri Q has what? Why did I do what I did? P tri. I meant the other one. So if you have y squared plus, so you have y squared composed y cubed plus 1 versus y squared tensor y cubed plus 1. What's the difference between those? Why are they related? This says they're related. Why are they related? So in one of them you have y cubed, you have this thing. So you have y to the 6th plus y cubed plus y cubed plus 1. And in the other one you have this. It's in-depth, meaning that you just have to put one on top of the other. Or you could have done it like this because it's symmetric. Sorry. could have put it in either order, but they're in depth. It means that I have all these open leaves, but I have to put the same one on each leaf.
Uh-huh.
And that's why this one's like always bigger than this one.
Right, okay, okay.
It always has more, at least as many summands, because the summands of this that come from this are the ones where on all the leaves, I couldn't do this trick. I had to use the same one every time.
Yeah, but just for the record, no one said, I thought you said, or Sophie.
No one said it's nice, so.
No one said it's an identity or an ISO.
No,
It's
no.
just I got tripped up because it's the same object.
Yeah,
on
yeah,
either side.
yeah. Okay, great.
Could you
Repeat the difference
offer
here?
that insight again?
Yeah,
That
the
was
difference between
really-
trie and tensor
Yeah.
is the tensor has an independence to it.
Yes.
This one can't depend on the leaf. So over here in y squared composed y cubed plus 1, we had 4 different summands,
Yeah.
but 2 of them had like mixy stuff in them.
Yes. Yes.
Tensor just has 2 summands because we're not allowed to mix. We either have to put y squared, like y cubed on both, or 1 on both.
That's a massive goal for me.
Okay, awesome.
Okay, I see, okay.
Okay,
Something, yeah,
okay, great.
unlaunched.
I'm sorry, I missed that, David.
Oh, does someone want to explain it real quick?
Yeah,
Or you want me
so-
to?
So you said you have to, with tensor,
With tensor,
so there's this difference in
It-
your degree of freedom you have with tensor on the one hand versus composition product on the other.
yeah,
With tensor, you're obliged to put all things like from the right there on top of the things to the left is what.
it has to be independent of your choice of leaf
Yes, exactly. Whereas that's not the case
for trie.
for try.
Yeah.
Yeah. Okay. I thought you said the reverse. That's
No,
why I was
yeah, okay.
confused. Yeah. Okay. Great. Thank
If I
you.
did, I didn't mean it. Okay.
David, before you erase that board, can I ask, the product of those 2 polynomials right in the middle of the board, is the last term supposed to be y to the 1?
Oh, yeah, yeah,
Okay, no,
yeah,
just making
yeah,
sure that I
yeah.
understood.
Good catch.
Could I ask something else that oh, sorry.
Yeah. Great.
Yeah. Could I ask something else that confused me about
Yeah,
tensor
Yep.
and composition?
yeah,
So David, if I have P and Q as polynomials,
yeah,
and I have P tensor Q.
mhm.
I'll take a photo of the corrected board so I can. That's okay. Yes. Yes. Thank you. If I have polynomial P and I have polynomial
Q,
Q, okay, so I get all combinations by tensoring them, P tensor Q, I get all combinations of those trees, right? I get,
I mean, what we were writing before with tensor
yes,
was like,
yes.
I just wrote a dot with 6 things on it.
Yep.
But over here, what we're saying to do is, no, what we're going to do is pop this one on top in all 3 places.
Exactly.
Yeah. But that point of view is like, is kind of using this embedding, is like thinking about it in terms of that. Yeah. We can
Right.
think of multiplying the number of leaves as like popping the same number on, popping the same one on each.
Yeah, okay, so that embedding up there
Yeah.
that you have,
Yeah.
I thought you'd said tensor in a way forces you to consider all combinations, whereas with triangle, you can be more judicious about the combinations you're taking.
Well, wait, no.
Okay,
You're using the word all and judicious in a way that
Yeah.
confused me. But
okay,
here,
yeah.
yeah, you take pairs of things,
Yes.
one from each,
Yeah, for tensor,
for tensor.
Yeah.
Sorry, and you
yes,
put this same one on all the open leaves.
that's right, that's right,
In this one, you could be more judicious.
that's what I meant, yeah,
Yeah. You take.
yeah,
You don't take pairs. You don't take pairs. You take this one, and then for every open leaf, you pick one of
You
those
pick
to.
one
Yeah.
of those.
Yeah.
right, and so, in what sense, so now, if we consider that embedding, it would seem that over on the left-hand side, we have some things that don't fit in over on the right.
No. These are ones where you're just picking the same one each time.
Right.
But that's a perfectly valid way of picking the same one, picking one for each one.
Okay,
You just pick the same one each time.
okay, okay. So that mapping, that's a polymap, right?
Yeah.
That's a polymap. Oh, oh. Okay, it's just like on the right-hand side, I would think, again, you said like with P composition, P tri Q, you pick which ones of Q go for which ones of P, right?
Yeah.
So isn't it like mapping I was gonna say non-injective.
But don't you see this picture here? Like we have this one there and
Yeah.
this one there.
Yes,
And we don't have either of these two.
yes, exactly.
Yeah.
Yeah, so on the left-hand side, we have more combinations than we do on the right-hand side, if that.
No, sorry. Tensor is the left-hand side. Tensor is the one with fewer.
Right, so it is more combinations.
Fewer combinations.
Oh, I see, okay, yeah, I got it.
Okay.
Pure positions.
Fewer positions, yeah.
Yeah,
I have a comment.
Yeah.
With a question.
Yep.
So, the dependy stuff.
Yep.
The dependy.
The ones that aren't independent, yeah.
Yeah. Because that relates to how in functional programming we talk about how monads are things that can depend on their output.
Yeah.
Which is why tri-monoids are monads.
Yep.
And why tensor monoids
Are just applicatives.
are
Yeah.
applicatives.
Yeah.
But aren't monads just any monoid in the category of endofunctors? So
A monoid in the category of endofunctors under composition.
okay.
Yeah,
So tensor monoids are
Yeah, when
not-
someone says monoid in the category of endofunctors, they are assuming you must know that they're talking about composition as the monodal product.
Okay.
But it's not, you could have been talking about sums, if
Yeah.
it's functors set to set, so yeah.
That's where you get the dependy both in Haskell and here. This dependy notion that it's
Yeah.
weird.
Yeah,
That's really good.
good, I'm glad. Okay. So in fact, like we have a lax monoidal functor from poly y tri to poly y tensor. So indep gives us one of these, and that means it takes monoids to monoids. Now, you might look at this and say, isn't that backwards? But the way, if you look at what lax monoidal functor means, this is the correct direction. And what that means is whatever monoids are in here, they're going to give us applicatives. And I think, but the next thing to do, or tensor monoids, the next thing to do is talk about, I think that there's a couple things I want to do, but one of the next things, I guess after lunch, let's talk about monoids in here. These are monads. Okay, so that's kind of the big next thing. And so monads give us applicatives and things like that. Co-applicatives give us co-monoids. But we don't, okay. Okay, so this thing just sends a polynomial to itself, but it has the property that P1, identity of P1, tensor identity, why am I writing indep? I guess I'm supposed to say indep here. Ugh, I don't know. It's basically on the polynomials, it's identity. So identity on P1, tensor identity on P2, maps to identity on P1 tri P2. And that's, the indep is the lax monoidality of this map. If that's confusing, don't worry about it. It's like the highbrow and lab version of why tri-monoids give you tensor monoids.
Wait, so what's the functor here?
Identity. But all it's switching is the monoidal product. It's saying I can think of, this is indep. It's identity on here, but the lax monoidality structure is about indep. Okay. Okay, what I wanted to talk about was something I wrote on the board like sheepishly the other day because I was like, oh, I just want to write this really bad, but yeah. So the thing I was writing, P1 composed P2 times Q1 composed Q2 maps in a nice way to P1 tensor P2 Q1. And I'm still not going to really tell you why I love this so much. That'll have to wait till monads. But it's pretty good, pretty interesting. P1 tensor Q1 P2 times Q2. And P1 composed P2 times Q1 composed Q2 also maps to P1 times Q1 composed P2 plus Q2. And so if you combine these into one formula, you see something that has all three, which I don't know, maybe there's only I love this because it's kind of just a weird fact in some ways. But I've never seen a formula that has three monoidal structures in it. So this goes to P1 tensor, sorry, 4 monoidal structures in it, composed P2 times Q2 composed P3 plus Q3. It's just kind of weird to see like 4 monoidal structures in a formula. And I don't know. So if you had like even more of these, you'd put tensors as long as you want, then a single times, and then pluses as long as you want. So it's kind of a weird fact. It's not weird. This one comes from day convolution. Tensor is day of times, and this one is times is day of plus. So they're very like, these are not weird things. These are like almost definitional. These are almost like getting down to very, to definition of tensor and times. But we'll have to wait till later. I hope I get a chance to tell you why I think they're cool. But I just want, now we can really do it because now we have try. Do you want to, actually, would it be a nice exercise to get the map? Should we write the map using, okay, let's try to write the map using our newfangled, trying to just write things, right?
This one says that it is a ordering.
That was a thing for you, yeah. I erased something, sorry everyone. Yeah, what was your question?
This kind of says there is an ordering tensor.
Tensor times plus,
Times
yeah.
Followed by plus
Yeah.
in a
Yeah.
big formula.
Yeah, tensor is, yeah. In some sense, if you start with 0 and the empty category, and you take the coproduct completion of its opposite, you get 1. If you take 1, take the coproduct completion of its opposite, you get set. If you take set, take the coproduct completion of its opposite, you get poly. Each time you do this, all your old tensors are preserved, and each time you get a new plus because you did a coproduct completion. And tensor comes way back from the unique monoidal structure on 1. It just keeps, it turns into times next, and then it turns into tensor. Times comes from the unique, times comes from like the plus that you just introduced at set,
Yeah.
and plus comes from the new plus that comes. So this is the oldest one, this is the second oldest, this is the newest, and some weird coproduct completion of opposite.
So how far does it go?
You can keep going. You just keep coproduct completing the opposite, and you keep getting more and more structure. And I don't know what those structures do. And at some point, people were thinking, around here, were thinking like, there's so many structures that start coming out, and they interact in really weird ways that, you know, like crystalline.
Like an infinity opposite coproduct completion?
Yeah, yeah.
So is try the day of?
No, try is not day of anything. Try comes when you do this move twice to anything. If you do coproduct completion of the coproduct completion of the opposite, you get the distributive completion.
And it's just like an emergent thing that.
Yeah, and when you do it twice to something, you'll get a new try operation, a new composition thing. Yeah.
So I'm sorry, so you said you
No.
start with category 0 and you do coproduct completion of its opposite, you
Yeah.
get 1.
Yeah.
You start with category 1 that you got from that, and you do coproduct
Completion.
completion of its opposite, you get set.
Set.
You start with set and you do coproduct completion, you get poly.
Of its opposite, you get poly. Yep.
And you were saying that there's this kind of successive,
Any old monoidal product you had
yeah.
will give you a new monoidal product. Like you'll be able to take old ones and like carry them forward through this procedure to get new ones. And when you start with the unique, so the category 1 has all possible structures and all possible properties. If you say, wait, what do you mean? Does it have limits? Yes. Does it have colimits? Yes. Does it have a monodal product? Yes. Is the monodal product duoidal with itself? Yes. Any property, it is true. All things are true. False is true. And there's nothing interesting. Everything's true. It has all structures and all properties. And the unique monoidal structure on the one object category carries forward under this procedure and eventually becomes tensor. And each time you do this procedure, you're going to get a new thing called plus. And so plus will be the new one that you get when you do it 3 times, and times will be the one you get it from the old plus, and tensor will be from the oldest plus. Okay.
Every 2 times you do it, you get a new.
And every time 2 times you do it, you get a new try.
What do you get?
I believe. I mean, it's been a while since I've thought about this, but I think so. Yeah.
What do you get every 3 times?
I don't know. Okay. So should we try writing down? Yeah.
I don't know your suggestion of that, but you can certainly think it's a good idea.
Okay.
I think it'll be good by
You what?
I think my thing will be
Covered later? I don't know if it'll be covered later. So who would be interested in like trying to watch me attempt to notate this, or walk through it with fingers pointing?
I want to see you notate it.
Okay, well then pick which one?
Spoken like the first one.
The first one. Okay, we're going to try to notate the first one. Okay, we'll call it phi. So phi on positions takes a position of I. What did I do? Position I of P1, and a function that takes P1 bracket I, 1 to P2 of 1, comma, I J1 of Q1 of 1, and J2 that takes Q1 bracket J1 to Q2 of 1, and sends it to, okay, I need a position of P1 and a position of Q1.
You have them.
Okay, I1, J1. And now given, I need something that takes a direction P1 bracket I1 times P2 Q1 bracket J1 to a position in this one, which is P2 of 1 times Q2 of 1. Well, let's just use I2 times J2. And that's on position. And then we have a direction here, and a direction is a D1 in P1 of I1 and a D2 in Q1, an E1 in Q1 of J1, and a direction in this or a direction in this. So X is in either P2 of, P2 of I2 of I1 or Q2 of J2 applied to J1. You tracking? Anyone who wants to be? Okay. Okay, so we have a D1 in P1, a direction of P1, an E1 a direction of Q1, but we have either a direction of P2 or Q2. Which direction should you send it to here? Whoever wanted this, what do you think?
I'm a little
Where are you lost?
I mean, the first, the map on positions is fine, the map on directions I kind of got lost with.
Okay, on directions, we need a direction of this.
Yeah.
That's a direction of this and a direction of this.
Yeah.
Agreed? So we picked a direction of this one. That's a D1, E1, and P1, I1 times Q1, J1.
Okay.
And then we need a direction of this. Well, I didn't know what to call it because it's either in left or in right.
Yeah.
It's either from P2 or from Q2. So I'll just call it X, unknowing which side it's on.
Yeah.
And now I need to send it back
Okay.
to a direction here. But a direction here is either direction here or a direction here.
Oh, I see.
Which one should I use?
The one that matches, right?
Yeah. So if X is in P2 of I2 of I1, then do one thing. But if X is in Q2 of J2 of I2, do a different thing. If X is in the P2 side, did I do a thing?
No, I missed.
If X is in the P side,
Yeah.
then use, any ideas? D1, and I need a direction in P2. Just X.
Oh, yeah.
X already is there. Yep. E1 X.
Okay. Yeah, I think that makes sense.
Okay. Okay, so it's basically lunchtime. Any last questions?